Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. My name is Edward Danurwenda Iskandar, with student number 12 12 30 1987. On this special occasion, I would like to thank you, Mr. Harry, for giving me the opportunity to explain about the journal that I'm about to explain. Today's review is about thermal equilibrium time as a novel characteristic of nanofluid evaluation, an experimental investigation of the still water-based binary and ternary nanofluids. First, we have the purpose. There is two purposes on this art review is to develop development and validation of a novel instrument. The research aims to create and validate a cost-effective and accessible instrument to evaluate the thermal energy transfer potential of nanofluids by measuring the time taken to reach thermal equilibrium. And the second one is optimization of nanofluid composition. The study seeks to identify the optimal combination and concentration of nanoparticles, MWCNTs and MGO-NBN, in binary and ternary nanofluids to enhance thermal conductivity and energy transfer to energy storage application. The increasing demand of energy application, particularly in renewable energy, has driven researchers to enhance heat transfer fluid by improving their thermophysical properties. Advances in nanotechnology have led to the development of nanofluids, colloidal dispersion of nanoparticles in conventional base fluids that exhibit superior thermal performance compared to traditional fluids. Nanofluids, such as those incorporating carbon nanotubes, CNTs, graphite, and metal oxides, have demonstrated notable enhance in thermal conductivity, heat transfer efficiency, and fluid stability. These improvements are often achieved through two-step synthesis methods using ultrasonic wave surfactants or pH variation to ensure stable dispersion. Hybrid nanofluids combining multiple nanoparticles in binary or ternary systems show even greater potential by improving rheological, tribological, and thermal properties. Studies have reported significant increase in thermal conductivity, heat transfer rates, and reduction in viscosity with hybrid nanofluids, such as multi-walled carbon nanotubes combined with magnesium oxide, MgO, and boron nitride, BN, or other nanoparticles despite their promise. Challenges remain in accurately measuring thermal conductivity due to the high cost, limited availability, and calibration requirements of traditional instruments. These limitations become particularly pronounced when testing nanofluids across various concentration and temperature ranges. To address these challenges, this study proposed an innovative approach by designing a novel instrument that evaluates the thermal equilibrium time of nanofluids, offering a simpler, cost-effective alternative to traditional thermal conductivity tests. The research explored the thermophysical properties of hybrid nanofluids, focusing on ternary systems combining MWCNTs, MGO, and Boron, was the first time, as well as binary formulation. The study highlighted the synergistic potential of these nanoparticles, given their individual thermal capabilities, and underscored the importance of developing particles and efficiency evaluation methods for future industries and applications. This novel approach provide new perspective of assessing the thermal characteristic of nanofluids, addressing existing limitation in instrument and cost. So there's the material. We have nanoparticles, multi-wall carbon nanotubes, magnesium oxide, boron nitride. Second one, we have nanofluids preparation, distilled water, and gum arabic. And the third, we have ternary, 50%, binary 1, 2, and 3. Next, we have the research method. The research method employed in the study involved both experimental and analytical approaches aimed at evaluating thermal properties of various nanofluids, particularly focusing on their thermal equilibrium time. The first step is the method was the design and fabrication of a fluid thermal equilibrium tester, FTET, a novel low-cost instrument created to measure the thermal equilibrium time of nanofluids. The fluid thermal equilibrium tester system consists of two cylindrical containers, one filled with boiling distilled water and one of the other with a nanofluid sample. These containers are insulated and sealed to prevent heat loss, ensuring that the heat transfer is solely due to the interaction between the nanofluid and the distilled water. Temperature sensors were placed in both cylinders, and data was logged continuously to monitor the temperature changes. The time taken for the system to reach thermal equilibrium, where the temperature of the nanofluid and the water equalize, was recorded as a key metric to assessing the thermal efficiency of the nanofluid. The nanofluid were prepared using 4 different nanoparticle composite. We have the MWCNTs and magnesium oxide and the boron, each synthesized in both binary and ternary combination at 6 different volume concentration ranging from 0.05% to 0.5%. The nanoparticle were homogenized using an electrical shaker and ball milling technique. And the stability of the nanofluid was ensured by adding gum arabic as a surfactant. Sonication was applied to prevent nanoparticle sedimentation and maintain uniform dispersion within the base fluid. Once the nanofluid were prepared, they were introduced to the FTET or for testing. The procedure for each test involve filling cylinder A with the nanofluid and cylinder B with the boiling distilled water. The system was sealed and temperature were monitored until thermal equilibrium was achieved. The temperature in both cylinders equalized. The time taken to reach this equilibrium, thermal equilibrium time, was calculated and used as an indicator of the nanofluid heat transfer efficiency. Each test was repeated under controlled condition to ensure repeatability, with the system allowed to cool room temperature between tests to maintain consistent condition. In addition to the experimental setup, the study used thermodynamics modeling to analyze the best heat transfer characteristic of the nanofluid. Equations were divided to calculate the heat transfer rate, heat transfer coefficient, and heat transfer and specific heat of nanofluids based on their thermal behavior during the test. The thermodynamic model took into account the heat transfer from the boiling water to the nanofluid as well as the specific properties of the fluids involved, including their density, specific heat capacity, and thermal conductivity. An uncertainty analysis was also performed to assess the reliability of the results. This analysis calculated the potential measurement errors in temperature readings and heat energy calculation, ensuring the precision of the data obtained. Overall, the research method integrates experimental testing using the FTET, theoretical thermodynamic modeling, and uncertainty analysis to provide a comprehensive evaluation of nanofluids thermal performance. This approach allows for a cost-effective comparison of various nanofluids, facilitating the selection of the most thermally efficient fluid for specific application. And the result, this study examines the density and specific heat of 24 nanofluid samples, comprising 4 ternary and binary nanofluid samples and nanoparticles dispersed in 6 volume concentration 0.05 to 0.5%, conducted under consistent laboratory conditions at room temperature. The study highlights that combining nanoparticles enhance the thermophysical properties of heat transfer fluid, improving heat transfer efficiency. The density of specific heat of hybrid nanofluids are determined by the properties of the base fluid and nanoparticles, accounting for their respective volume concentration. Results show that density increases with volumetric concentration, while specific heat decreases inversely with volumetric concentration. Detailed data description. And the next we have the SEM analysis results. Scanning electron microscopy, which is, you can say it as SEM, was utilized to analyze the microstructure and morphology of prepared hybrid ternary and binary nanoparticles. The nanoparticles examined include MWCNTs, magnesium oxide, boron, and magnesium. High-resolution SEM image at 30 kilovolt and 5 ohm revealed the homogeneity of nanoparticles after pre-shaking and milling, compared to the original state before synthesis. Additionally, SEM image after ball milling process captured at varying resolution 50, 20, and 5 and 2 further demonstrate the microstructural characteristic and uniformity of the nanoparticles. The next one we have thermal equilibrium time and temperature. The experiment evaluates the thermal equilibrium time of synthesized ternary and binary hybrid nanofluids using a fabricated FTET instrument, comparing them with distilled water as the base fluid. There is number 1, ternary hybrid nanofluid exhibit the shortest TET, confirming superior thermal conductivity and heat transfer enhancement at 0.5%. Volume concentration, it reached equilibrium in 157 seconds, 112 seconds faster than distilled water. Binary hybrid nanofluids, equilibrium time of 198 seconds at 0.5%, 71 seconds faster than distilled water. Equilibrium time of WCNTs with boron, equilibrium time of 179 seconds at 0.5%, 90 seconds faster than distilled water. And we have magnesium oxide with boron, equilibrium time of 230 seconds at 0.5%, at 39 seconds faster than distilled water. The third, volume concentration impact, higher volume concentration at 0.5% consistently reduce TET compared to lower concentration for all nanofluids. And we have comparative behavior. Binary WCNTs and boron at 0.4% showed behavior similar to ternary MWCNTs, MgO boron at 0.05% with only a 2 seconds TET difference. Similarly, binary MgO boron at 0.5% resembled WCNTs MgO at 0.05%. Distilled water reference, distilled water had a TET of 269 seconds, significantly slower than all tested nanofluids. Overall, the ternary hybrid nanofluids, WCNTs, MgO-BNs, and boron demonstrate the best thermal performance, highlighting its potential for enhanced heat transfer application. Next, we have heat transfer. The study evaluates the heat transfer potential of various nanofluids, specifically focusing on the heat transferred from the initial to thermal equilibrium stage. The heat transfer was calculated for different nanoparticle combination and binary hybrid nanofluid at varying volume concentration. The maximum heat transferred to the nanofluid was highest of the ternary WCNTs, MgO and BN at 19.4 kilojoule, followed by the binary WCNTs, MgO at 17.7 kilojoule, binary WCNTs, binary boron we have at 18.2 kilojoule, and binary MgO boron at 17 kilojoule. In comparison, distilled water transferred 15.8 kilojoule of heat, making the nanofluid superior in heat transfer by 1.2 to 3.6 kilojoule. The study emphasized the increased heat transfer with higher volume concentration of nanoparticles as transferred with higher volume concentration of nanoparticles, as shown in figure 15, where the thermal equilibrium time decreased with increasing volume concentration, indicating enhanced thermal conductivity overall. The ternary WCNT, MgO, and boron nanofluid exhibit the best thermal properties, including heat transfer and thermal equilibrium time, compared to the other nanofluids. Validation of the FTET instrument. The study aimed to validate the FTET instrument by testing the thermal conductivity of various nanofluids with a 0.5% volume concentration. 4 nanofluid samples were tested at temperature of 25, 35, and 45, and 55, using a KD2 device for measurement. The result showed an increase in thermal conductivity with temperature for each sample. To further validate the FTET instrument, the heat transferred by the nanofluid was compared with their thermal conductivity. The study found a strong correlation between the thermal conductivity curves and the heat transfer value, confirming the accuracy of the FTET instrument. The thermal conductivity of samples was ranked in order of D, B, C, and A. This verification supports the validity of the FTET instrument created in the study. Next, the conclusion of the journal is the study introduced a novel experimental instrument designed to assess the thermal potential of nanofluids based on their thermal equilibrium time, TET. This based on their thermal equilibrium time. This new instrument enables a straightforward, cost-effective means of evaluating nanofluid thermophysical properties, particularly in the context of their ability to absorb and transfer heat. The TET is a new characteristic that measures the time it takes for nanofluid to reach thermal equilibrium, which directly correlates with the fluid ability to conduct a transfer heat. This novel approach addresses the challenge of relying on expensive and often inaccessible instruments for thermophysical measurement, offering an affordable alternative to researchers and enhancing the accessibility of nanofluid research. Thermal equilibrium time as an indicator of conductivity. The thermal equilibrium time emerged as a crucial metric in the study, demonstrating that nanofluids with higher nanoparticle volume concentration reach a thermal equilibrium faster, which indicates better thermal conductivity. The faster a nanofluid reaches equilibrium, the more heat it is able to absorb and transfer in a given time. This aligns with the fundamental principle that fluids with higher thermal conductivity are better suited for heat transfer applications, including those in energy storage systems. Among the nanofluid studied, the ternary hybrid nanofluid, MWCNTs, MGO-BN, with a 0.5 nanoparticle volume concentration, showed the shortest TET taking just 157 seconds to reach thermal equilibrium. This result not only highlights the superior thermal performance of this ternary nanofluid, but also underscores the potential of hybrid nanofluids in enhancing heat transfer. Third, performance of the binary and ternary nanofluids. The study compared the performance of various binary and ternary nanofluids with different nanoparticle combinations, namely MWCNTs and MgO and boron, the MWCNTs and magnesium oxide, MWCNTs and BN, and MgO and binary. Among the binary nanofluids, the MWCNTs and boron mixture provides to be the most efficient in terms of heat transfers, achieving a TET reduction of 31% compared to distilled water. This was followed by MWCNTs, MgO, and MgO-BN, which had reduction of 23.8% and 11.5% respectively. However, the ternary nanofluids, MWCNTs, MgO-B, and BN, at 0.5% concentration, outperformed all binary mixture, demonstrating 8.3 more heat transfer than MWCNTs, MgO, at 5.8% more than MWCNTs combined with boron, and 11.8% more than magnesium oxide combined with boron. The superior thermal performance of the ternary hybrid nanofluid is attributed to the synergistic effect of combining three different nanoparticles which enhance the overall heat transfer characteristic more effectively than binary mixtures. This study emphasized the concept of nanoenergy in the context of nanofluid heat transfer. Nanoenergy refers to the heat energy transfer by nanofluids that exhibit superior thermal conductivity due to the presence of nanoparticles. The ternary hybrid nanofluid, particularly the MWCNTs, magnesium oxide, and boron mixture, not only reach thermal equilibrium faster but also transport 18.5% more heat than distilled water, demonstrating the significant potential of nanofluid for improving heat transfer. This increased heat transfer capability is especially more for applications like energy storage, thermal management, and heat exchangers, where maximizing energy efficiency is a crucial part. This study also clearly established a correlation between volume concentration and thermal performance as the nanoparticle concentration in the base fluid increased. The thermal equilibrium time decreased, meaning the fluid reaches thermal equilibrium more quickly. This implies with higher concentrator nanofluids have better heat transfer performance. Specifically, a 0.5% volume concentration was identified as the most effective for achieving optimal thermal performance. The study concludes that increasing nanoparticle concentration leads to a corresponding enhancement in the nanoenergy heat transfer by the nanofluid, which is essential for improving the efficiency of heat transfer system. The uncertainty analysis conducted in the study indicates that experimental instrument developed for this research is highly reliable, with an average error margin of 0.936% across all the tested nanofluid composition. This low error margin reinforces the validity of the instrument results and demonstrate its accuracy in measuring the TET of various nanofluids. The instrument's high level of precision makes it a valuable tool for future comparative analysis and for researchers who need to evaluate nanofluids performed without resorting to costly and specialized equipment. One of the major contributions of this study is the demonstration of the cost effectiveness of the new evaluation instrument compared to existing methods for thermophysical testing. Traditional thermophysical tests are often expensive, require specialized laboratory facilities, and involve complex instrumentation. The new instrument, by contrast, offer a much more affordable alternative that can be fabricated in a relatively low cost and is easily accessible to researchers worldwide. This affordability, combined with the accuracy of the result, positioning the instrument as a valuable resource for advancing nanofluid research, particularly in resource-constrained environments. The study recommends that further research be conducted to explore the thermodynamic models underlying the behavior of nanofluid including the estimation of heat transfer coefficients for various nanofluid composition, such as models could help in better understanding the mechanism that drive enhanced heat transfer and could lead to the application. Additionally, a comparative analysis of different types of nanoparticles, their combination and their concentration could help optimize the design of nanofluids for various thermal management applications. So what are we trying to achieve in this journal is it aims to introduce and validate a new instrument that measure the thermal performance of nanofluids, providing an innovative way to assess their heat transfer properties based on the time it takes for the fluid reaches thermal equilibrium. This new metric thermal equilibrium time is a unique approach that can help researchers evaluate the comparative thermal efficiency of nanofluids in a simple, cost-effective manner by focusing on TET, and study provides an alternative to more complex and expensive method of evaluating nanofluid thermophysical properties. Second, enhancing heat transfer efficiency in energy storage and conversion. The journal seeks to demonstrate the potential of nanofluids to enhance heat transfer in energy storage and conversion system by testing various nanofluids, especially hybrid nanofluids composed of multiple nanoparticles. That the study explores how nanofluids can be engineered to improve the efficiency of heat transfer process, which is crucial for optimizing energy systems like solar thermal energy, thermal storage tanks, and heat exchangers. The research provides a comprehensive comparative analysis of binary and ternary nanofluids with different nanoparticle combinations, such as MWCNTs, magnesium oxide, and boron. It aims to establish which nanofluids perform the best in terms of heat transfer thermal equilibrium time, thus offering a benchmark for future equilibrium time research in nanofluid development. This comparative framework is intended to assist researchers in selecting the most appropriate nanofluid for specific application based on its thermal process, providing a reference for future studies by introducing a new way to measure, compare the thermal efficiency of nanofluids. This journal sets a foundation for future research. The study's results and developed instrument can serve as a reference for future comparative studies on nanofluids. Researchers can use the findings and methodology presented in this work to conduct further investigation into the thermodynamic properties of nanofluids, ultimately leading to the optimization of nanofluid formulation for improved thermal management. This journal advocates for more in-depth studies in the thermodynamic principles that govern the heat transfer properties of nanofluid. Future work could involve investigating the heat transfer coefficient, the viscosity of nanofluids, and other factors of influence their thermal conductivity, such as research could help refine the use of nanofluids in practical application and led to development of tailored nanofluid formulation for specific engineering challenge in energy system. The journal presented in an innovative approach to evaluating comparing nanofluids using a new instrument that measures thermal equilibrium time (TET). The findings demonstrate that ternary hybrid nanofluids, particularly MWCNTs, magnesium oxide, and boron, are highly effective in enhancing heat transfer efficiency with the ability to reach thermal equilibrium faster than the traditional fluids like distilled water. The study emphasized the importance of nanoparticle concentration and nanoparticle combination in optimizing nanofluids performance. Additionally, the journal highlights the affordability Additionally, the journal highlights the affordability and accuracy of the developed instrument, offering a promising tool for researchers in the field of nanofluid technology, especially for the energy storage and conversion application. So this is the journal that I'm currently reading about. And that's all for my presentation. Thank you for your attention.